Hello. In this lecture, we'll see a little bit on pulse width modulation. To cover this, we should know two important parameters. One is the frequency at which you are operating the pin, and one is the duty cycle. Duty cycle is nothing but how much time you are on and how much time you are off. Suppose you are on for 50% of the time and 50% of the time you are off, then we say the duty cycle is 50%. To see it much elaborately, let us consider we have a pulsating waveform which is having a duty cycle of 50%, varying from 0 to 5 volts. Now, what will be the output voltage on an average? Is actually a multiplication of the duty cycle. So, it will be V out is the maximum voltage into your duty cycle. If the duty cycle is increased, you will have a increased brightness of your LED. If your duty cycle is reduced, you will have a reduced intensity of your LED. This is what really happens during a pulse width modulation. So where does this application find usage? Like you will find mostly the applications are in LED dimming, and the same can happen with the motor speed control also. If the duty cycle is more, your motor speed will be more. If your duty cycle is less, your motor speed will be less. Same can be applied there also. So ahead, you can observe the LED which is there. So what all pins are supporting this pulse width modulation on Node MCU board are these GPIOs 0, 2, 4, 5, 12, 13, 14, 15. These all support the pulse width modulation. These are the actual GPIO numbers. If you see on the pin numbers, it will be D3, D4, D2, D1, D6, D7, D5 on the Node MCU board. You can observe here. Okay. Now in our exercise, we'll try to perform this pulse width modulation over an LED, onboard LED which is present near to the PCB antenna, which is actually connected to GPIO2. Now, as like previously I have created a project, I will create a lab2, and you can go and check in the settings also. You will find the same settings like project structure excluding both these unwanted folders, and the project interpreter having the wanted modules, and frameworks MicroPython having the ESP8266 enabled with respect to COM device. Now you can also see my configuration having no problem. Okay, fine. Now we'll try to code for this pulse width modulation. Now what I want to simply do is import this machine module and time module. Now for this time we'll also import the math module. Next, as you know, this common kind of script we use usually for Python based scripts is like I want to know whether I was being called from the main module or being called from a different module. If and only if I was called from main module, I will be calling my main. Now what is my main is, I've taken an LED object in which I loaded this machine.pulse width modulation with the respective pin number. Thereafter, I want to call a function called pulse with this LED object being passed, and there is a delay that I want to pass. This 200 is a parameter which I want to specify the delay between the brightness variations so that I can clearly see my brightness variations. And what is pulse now? Pulse function is nothing but here I'm trying to change my duty cycle in a sinusoidal fashion. How come is I just use a math sine function from the math module, and this sine I by 10 tells me how many number of steps I'm trying to take. So when it's like 20 by 10, so I can start from 0 to 20. So your resolution will be 20 steps. So the brightness control will be 20 steps. Note that as this being used as a sine function, now you'll have one upper cycle and one lower cycle. So you'll have 10 positive values, 10 negative values. Now I include a print statement which tells me properly what is the duty cycle I'm feeding, how the sinusoidal function has been varied with what kind of pi values, and what is the output of my sine function. Flash it onto the board. It's uploaded. You go to COM, Node MCU, load them. This time the device is COM4, open it. Now you see that the value inside sine function is 4.3 multiplied by 500 and plus 500, and this is the value which is the output of sine function. So which varies from -1 to +1. So I'll say a set of 10 values, and from again 1 to -1. So you'll observe these values being going from up to low. From 0 they'll go up to 1000, and from 1000 again I'm reducing the duty cycle, because of which I'll observe increase in the brightness and also reduction in the brightness. Okay, let us see how it happens. Now in order to show the difference, we shall just try to change the intensity levels from 10 to 5. We'll see what happens. Now let me change the intensity levels from 10 to 5. 10, and these are 5. And let me flash it again and see what happens. It's done. You can observe there is a different case here, where the number of intensity levels are reduced. So you can see the LED getting brighter very fastly. You can see the intensity levels are very less, so you don't see any too much variation. Now let me try one more thing. I'll increase the delay to 500. Let's see what happens. You can observe the delay between the steps of brightness is increased. This delay corresponds to that. Hope this explains very well. Now ahead we'll see how to deal with an RGB LED. Yeah, now we'll take an example of an RGB LED. In market you can get some varieties like this sometimes, which is having RGB and a common cathode. And like when I say the GT cycle is maintained, if you try to vary the intensities, you can see the intensities of red light, green light, blue light being changing. Now let's say this is similar to if we try to mix red and green in equal portions, we'll get yellow. Now what will happen if we mix 30% of green and 70% of red, we'll get a different color. Now we'll try to see how that can happen. So for which you can, this is an optional exercise. I did not mention you this hardware is required or not. So it's up to you. You can get a normal LED which is RGB LED in market directly, or you can get modules like this which have the limiting resistors. And now if you see the node MCU map, pin map, so D0, D1, D2, D3 are these names on the board, which are in fact GPIO 16, 5, 4, 0, etc. So you can observe this map. Now what I've done is I've connected an RGB LED like this to pins D2, 3, 4, or you can connect anyways, or you can, it's up to the code, you can change the code. As it being common cathode, I have connected the ground. Now if you see the breadboard layout, it can be like this. You connect the common cathode pin to the ground and remaining to the GPIOs. GPIOs are your choice, you can just change it in the code. Note that it cannot be any GPIO, it should be the GPIOs 0, 2, 4, 5, 12, 13, 14, 15, the pins only which support pulse width modulation. Now let us have a look at the code. What I have done is I have simply created 3 LEDs R, G, B and B. Now I have given the pin names 0, 4, 5. Now what I am trying to do is I am trying to make use of the red LED intensity variation. At the end of this variation, the red LED will be high, or it is completely eliminated. Now if you try to change the green LED color after red LED is being high, you will see different colors coming. That means a mixture of R and G with G varying its intensity. Then after and R and G will be high, B will be changing its intensity. And you can see a mixture of colors coming. We shall do this simple exercise. Only thing what I have done is I've created 3 LEDs and I'm using the pulse function one after the other. This loop will continue for up to 10 times and you will observe multiple kind of colors coming. Let us see. Yeah, the red is fully off and the red is high. I'm trying to change the intensity of green. You see different colors coming. Now green is also high. We'll change the blue. You see it? Now it comes a white color. So this way you can change n number of colors using pulse width modulation, one on RGB LED. Hope this explains. Thanks.